the 7th. It will cover chapters 1 and 2. We will get through the bulk of chapter 1 or chapter 2 today. We finished chapter 1. We will get through the bulk of chapter 2 today. We may have a little bit to finish up, and then I'm going to start chapter 3 material on Thursday. That won't be on your exam, but this means that you'll have most of your material to start studying after today's lecture. So that gives you extra time. Remember that I will bring calculators, so you can use a calculator. You can use scrap paper that you can bring. You can get I gave out 4x6 note cards. So on this note card, and I don't care if you write on the side with lines or if you write on the side that's blank. Most of the people write on the side that's blank because you can write real small and fit as much as you want. You put anything on that one side that you want. Just know that you're going to turn this in when you turn in your exam. Okay, so I suggest that you start sort of making a list of things that you would want to put on that note card. Maybe not finish the note card until after the lecture on Thursday so that you've got everything, so that you have everything in chapter 2 that you may want to add in there as well. If anybody wants extra time, especially if you feel like you move through things in math kind of slow, I will be here and sort of set up at 9 on Tuesday. So I will be in this room. And so if you want to come and have an extra half an hour, just so that you don't feel like the pressure of the 90 minutes trying to get the exam done, give you an extra half an hour so you can actually have a full 2 hours to take it. I'm fine with that too, okay? There's no one in here before us, so it works out fine. Just know that when you come in, there may be students taking an exam when you come in on Tuesday. So when you come in, just have your materials out that you're going to use for the exam. Don't bring all your papers and be making tons of noise. Try and sort of come in already prepared. Get yourself ready out there. And then just come in with your scrap paper, with your note card, with your pencil, calculator and such. Okay, I will have my calculators. I do suggest that if you don't have a calculator that you get one so that you are using the same one all semester. It just makes it much more familiar to you. If you use my calculators and you don't really know how to put scientific notation in or something like that, then that can be more of a challenge because you're not quite sure how to use that calculator. Whereas if you have your own, then we can go through and you can practice. Okay? All right, so information in chapter 2. So chapter 2 goes and looks at the building blocks of all matter. So remember, matter has mass, takes up space. So in the studying of particles and the studying of matter, they worked to smaller and smaller ideas, and they realized that everything has to be made of something. That there is something that makes up gases, something that makes up liquids as well as solids. And this led to this idea of the atom. So the atom is really defined as being the smallest unit of matter. When you look at things smaller, the subatomic particles, they don't have the same properties that elements like them have. So you have to look all the way down to just the atom size. Atoms that are the same element all have the same properties. There are 3 particles that make them up. And this combination of these 3 particles is responsible for whether an element's a solid, a liquid, or a gas, whether an element is reactive or stable, how heavy that element is, how dense that atom is compared to the space it takes up. So think of lead in comparison to aluminum. So the difference between them, because of the subatomic particles, that is the reason that they have these different properties. So we have 3 subatomic particles: protons, neutrons, and electrons. They have variations to them as well. Protons, they know, have a positive charge. Protons also have mass. Neutrons are a lot like protons, except from their name, what is their charge? They're neutral, right? So that's where the name kind of came about. So protons positive, neutrons are neutral, so they have no charge, but they have mass equivalent to a proton. So they're about the same. Electrons, on the other hand, they have the negative charge. Their mass is so small, it's really negligible. So remember we said that all matter has mass and takes up space. So electrons do have mass, or else they wouldn't be matter. But electrons are about 2,000 times smaller than a proton or a neutron. So in comparison, they would say it has relatively no mass. Electrons do not add to the mass of the atom as a whole. So other things that you can find out or you can describe in terms of protons and neutrons and electrons is their location. So in an atom, so if this was just a generic atom, this sort of circle space, they found that there is an extremely dense core, typically located about in the center. It's very small. They named this core the nucleus. Like what you have nucleus in the cell, sort of the center part. So they named it the nucleus. They found that this is where all the mass was located. A very dense core located in the nucleus. So what are the particles that are there? This is where your mass is. So what are the particles that have to be there? Not electrons, because we said relatively electrons have no mass. Okay, so they're not located in the nucleus. Instead, it's protons that you find in the nucleus and neutrons. Sometimes you'll see protons written as a P with a little plus, just as sort of a short abbreviation, and that tells you that charge. Neutrons, you'll see them written with an N with like a little circle, which means like neutral or no charge. Those are all packed into the very center part of the atom in the nucleus. Electrons, on the other hand, they're actually fill the rest of that space. So electrons are located outside of the nucleus. And I think of electrons as being like particles of energy. They're in constant motion. So they are outside the nucleus. So they don't stay in just one place. So this electron is constantly moving. So it's constantly moving in this pattern around the nucleus. It's negatively charged. It's attracted to those positive protons. But because of the fact that it's moving, it doesn't go into the nucleus and it doesn't move away. It's sort of held in that space because of that motion. Think about like the moon that orbits the Earth. Okay? Same thing. You have this attraction because of gravity, but because it's moving, it doesn't move further or away. It doesn't move closer. It keeps it in this orbital. So we'll talk a little bit more about electrons and how these electrons come into play. But once you know these things and you have a periodic table, you can identify the numbers of protons, neutrons, and electrons for any kind of element that you've got. Okay, so we've got the nucleus where protons and neutrons are clustered. You've got these electrons dispersed along the outside in like a cloud in constant motion. But most of the atom is actually empty space. So most of that space, those electrons are moving. So if you were to try to pinpoint where an electron was, it's in motion, so it's really impossible to do. This chart just summarizes just what we just said. Protons, neutrons, electrons, some of the symbols that you might see, the charge on them. Remember I told you that they're relative mass. So protons and neutrons have an actual mass, but they're super, 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 super small. Okay, so they're like 1 × 10 to the minus 27th grams is how much they weigh. So remember negative exponents? That would be a decimal place, 26 zeros, and then a 1. So that's so small. Trying to use that as a sort of functional unit is almost impossible. So that's why they came up with this. So a relative mass, they're just saying in comparison, if you look at all 3 subatomic particles, protons and neutrons have about the same mass. So we'll give them a mass of 1. We'll just say that their atomic mass unit is 1. And in comparison, the atomic mass unit, the atomic mass unit for electrons is 0. So they call these AMU. So they'd say that electrons have an atomic mass unit of 0 because it's so small, whereas we would say protons and neutrons are each equal to about the same relative mass, and we'd give them masses of 1. So carbon was one of the first ones that they defined, and so they, in measurements of mass of carbons, calculation of size of a carbon atom, they determined that a carbon atom has 6 protons and 6 neutrons. So they said, okay, well, each proton has 1 AMU, each neutron has 1 AMU, so that's going to give carbon a mass of 12. It's the protons and the neutrons just added together. It's also got 6 electrons. But those electrons really don't add in to the weight. They don't add to the mass because they're so much smaller than the others. So if you look on your periodic table and you look at carbon, and if you forgot your periodic table or you've lost your periodic table already, there's some extra ones down in this front corner that you can come down and grab one. You will need it in the calculations that you've got. So if you look at the periodic table and you look at carbon, what is the number that's above? 6. Okay, what's the number that's below? 12.01. So if you're looking at your periodic table, what is the 6 equal to? What we just talked about. Numbers of what? 6 protons. Okay, so you see that that's the same. This top number is the atomic number. The atomic number, by definition, is what defines the atom as belonging to a specific element. So in atomic number, this tells you the number of protons. So if you look at oxygen, how many protons does it have? 8, right? You just look at the periodic table, so it's not something you have to memorize. You just look at the whole number above the symbol. That is always going to tell you the number of protons. So the number underneath, it has this decimal place value. And if you look, except the really, really large elements, they all have some decimal place number. This is the atomic mass. Just knowing these 2 numbers, and you can tell me how many protons, how many neutrons, how many electrons in each. So here's the way to do it. First, atomic number is always equal to your number of protons. That's what determines what the atom is. So if I have an atom that has 17 protons, what element is it? If I have an element, so look at your periodic table, if I have an element with 17 protons, it's going to be chlorine. Okay, so you know, if you know the atomic number, you can identify what the symbol is. And if it's one of the ones you have to know, you can tell me the name. If you know the name, you can tell me the number of protons. because it's not carbon unless it has 6 protons. So that is really defined. Now, in a neutral atom, so as long as you're not talking about an ion, like a sodium ion or a chloride ion, as long as you're talking about a neutral atom, so if I just have an atom of carbon and it's neutral, then the number of protons has to equal the number of electrons because the pluses and the minuses are balance each other out to give me a neutral atom. So in a neutral atom, atomic number is also the number of electrons. So again, if I said you have a neutral atom and it has 47 electrons, what element is it? 47 electrons. That's one of those ones. Look on your periodic table. So 47, I think I gave you the right one. Yeah, so 47's Ag, and Ag is silver. Yes, it is silver. Very good. Okay, so if you know, like you should be able to like go back and forth. So these are super simple questions. So you'll see questions like that. But as long as you know how to use the periodic table, you don't have to memorize any of that. You just have to understand how to use the periodic table. Last one. So how do you find the number of neutrons? So you know that protons and neutrons have mass. Electrons are about negligible. So the atomic mass, which is the number at the very bottom of each block, round it to a whole number. That tells you the number of protons and neutrons. So if you take the atomic mass rounded minus the atomic number, that will tell you the number of neutrons. So it's super easy with the first ones, like when we have carbon, because we said carbon is 6 and 12.01. So how many protons? 6. How many electrons? 6. How many neutrons? Take 12 and 12.01, round it to 12, subtract 6, so it would be 6. Do you notice that if you look at these small ones, like nitrogen, it'd be 7, 7, and 7. Oxygen's 8, 8, and 8. Notice the small elements, they tend to have very similar numbers of protons, neutrons, and electrons. What about beryllium? So Be is 4. How many protons? 4. How many electrons? 4. How many neutrons? 5. Okay, just take 9.012, drop it off, round to 9, subtract 4, tells you 5. So the little ones, little elements, those that are in those first 4 rows, they tend to have very similar numbers of protons, neutrons, and electrons. So there's examples there. Lithium as well. So you see if you count in this one, you can see that lithium, which is number 3, and has 6.941. Oh, jeez. I don't know how I do it. Such a talent I have. So 6.941. So you would just take 3 protons. You see the 3 little red balls in the center in that nucleus. 3 electrons, the little teeny tiny blue specks outside of the nucleus. And then if you take 6.941, round it to 7, subtract 3, do you see the 4 gray balls that are in the nucleus right along with those protons? That nucleus is way smaller than they draw it. I mean, they have to like draw it big enough so that the balls look kind of like you can identify what they are. But in theory, they are so much smaller that nucleus only makes up about 1% of the entire atom. So let's do a couple of them. So silver. Go back. So complete these. Just wrote down there names and symbols for you. MD. All right, so how many protons in AG? 47. How many neutrons? A little louder. 61. Okay, how many electrons? 47. And what's it called? This is silver. Okay, so that's one of yours. Na. How many protons? 11. How many neutrons? 12. And how many electrons? 11. And it's called sodium. It's another one for you to know. TH. How many protons? 90. How many neutrons? 142. 142. How many electrons? 90. And it's, well, this is not one you would know. This is thorium. It's not one that I would ask you what its name is. Kr. How many protons? 36. How many neutrons? 48. And how many electrons? 36. This is krypton. Like Superman. Hg. How many protons? 80. Neutrons? What would you round that to? It'd be rounded to 201. So when I do the subtraction, what would you get? 121. Right? So it just round that decimal. If it's a half or higher, round that last number up to a whole number. And then electrons would be 80. And Hg is one to know. That is what? This is mercury. All right, and the last one. Zn, which has how many protons? 30. How many neutrons? 35. And how many electrons? 30. And it's called zinc. Yep, that's another one that you need to know. That was one on your list. You've got like a list of 30. So if some of those you're like, I didn't know that one. Make sure that you go back through on that periodic table chart in chapter 1 is where I have the extra 10. So you know elements 1 through 20 you should know. And then I gave you an extra 10. Zinc's one of them. Mercury is one of them. Silver, gold, copper, chromium, iron, iodine. Just trying to remember some of them. So make sure that you have those names and symbols down because you may see symbols instead of names for some of them. And you may be asked to identify what the symbol means. So that's super easy, okay? Everybody got that? So it's really super easy to figure out protons, neutrons, and electrons. All you gotta have is a periodic table. So what does this mean? Well, there are a couple of different ways that you can actually write elements. One way is called symbolic notation. Symbolic notation puts the symbol, the mass number, the atomic mass is listed above in front of the symbol. The atomic number is below. Now do note, this looks different than the periodic table, which looks like this. In the periodic table, the atomic number is on top. In symbolic notation, the atomic number is below. I didn't write those rules. Like that seems like completely backwards. Yes, I would have kept it the same way or changed my periodic table and listed it that way. But just know it's actually the reverse. So just remember the bigger number is always the atomic mass. The larger number, whether you see it written on the periodic table or if you see it written as symbolic notation, But what this tells you specifically in symbolic notation, this is actually giving you information about a single atom. And so looking at a single atom, we can define the numbers of protons, neutrons, and electrons, and the neutrons is a whole number. So notice that the atomic mass there is a whole number. The mass number is protons and neutrons. The atomic mass is just those protons. The reason that the periodic table has those decimal places in the atomic mass is because there can be elements or atoms of carbon that have 6 protons and electrons, but have different numbers of neutrons. And so in this, these are called isotopes. Atoms of the same element with different mass numbers have different numbers of neutrons. They still have the same properties that carbon atoms have, but instead of 6 protons, 6 neutrons, 6 electrons, there are very small quantities of carbon that may have 7 neutrons. There's even smaller quantities of carbon that may actually have 8 neutrons. They call these isotopes. So it's when you have an element with different numbers of neutrons, and so therefore they have different masses. So in the symbolic notation, like I wrote it this way, that's carbon with 6 protons, 6 neutrons, 6 electrons. This is a carbon atom with 6 protons, 6 electrons, but 7 neutrons. So notice that that mass number is 1 greater. The other ones always stay the same. If it didn't have 6 protons, it wouldn't be carbon. So it's got to have an atomic number of 6. In fact, there exists atoms of carbon that have a mass number of 14. That's right. Because if it was atomic number 7, that would be nitrogen, right? If it's atomic number 6, it's carbon. It can have varying masses because it has varying neutrons, but the number of protons has to be the same.
So does that mean that neutrons has the least effect on the structure and function of the element?
No. No, and that leads into the next topic. Okay, so hold on. Another way that you might see them written is this. Carbon 12, carbon 13, and carbon 14. It's just another way of trying to identify an isotope. That's the symbol's name with the atomic mass behind it. Okay, so that's the mass number, because you know carbon's going to have 6 protons, but it could have a variation in terms of mass. Now, if you look at where the average atomic mass that came up for carbon, like I told you, so carbon on the periodic table is C6, 12.01. The reason that it has the 12.01 is because it's actually the average of the masses compared to their abundance. So if you look, you see that 99% of carbon atoms are carbon 12. 6 protons, 6 neutrons, 6 electrons. There is a really small percent, just under 1%, that is carbon 13. So that has 7 neutrons, still has 6 protons, 6 electrons. There's a really, really small number of carbon atoms out there that are called carbon 14. Carbon 14 actually has 2 extra neutrons than normal. That has 8 in comparison to the normal 6. Carbon 14. Yeah, so when they talk about carbon dating, That is using carbon-14. And it's because of the next topic, because carbon-14 has 2 extra neutrons than normal, and that makes it unstable. So it breaks down over time. It's radioactive. And when it breaks down, it releases energy. So we can actually measure the amount of energy in a sample and determine how much carbon-14 is present. Okay? So yes, so we're going like rolling right through. That's the only thing that you really need, I want you to understand, is that the reason that the periodic table has those decimal places is because it's really an average of the isotopes for that element. So carbon-12 has 6 protons, 6 neutrons, 6 electrons, right? Does that make sense? So carbon-14 has 6 protons, 6 electrons, and how many neutrons? 8. So it has 8. They only differ by numbers of neutrons. Isotopes only differ by numbers of neutrons. So carbon-12, carbon-13, carbon-14, they just differ by a neutron or 2. But the majority found on Earth is carbon-12. And that's why the atomic mass really tells you the mass of the most common isotope. So if you were to look at, so say bromine, Br. So bromine is 35, and its mass number is 79.90. So the most common isotope, what would its mass be? 80, yeah. The one closest to the whole number. The most common isotope, just round it up, right? So 79.9, I'd round it to 80. So I would say that bromine 80 is the most common isotope, just from looking at the periodic table, because it's a relative atomic mass. Just round to the nearest whole number. That is why we would say that carbon-12 is the most common isotope, because that's the nearest whole number for the atomic mass that you find on the periodic table. So that could be another question that you might see, okay? What's the most common isotope of gold? And so you would just find gold, which is 79. You'd find 197.0, and you'd say it's gold 197. Right? That'd be the closest or the most common isotope, just round to the nearest whole number, and that'll tell you that.
Are we going to get to how exactly the numbers of the neutrons affect the properties of it?
Yeah, so that's next. Hold on. Okay, so somebody asked about carbon-14 and then asked about numbers of neutrons. Did I skip a page? I must have skipped a page. Elements that are large, they have lots of protons and neutrons. And where are these located? They're in the nucleus. And remember, I told you that these are really dense. So as protons and neutrons pack in, isotopes have different numbers of neutrons. Large isotopes, so when you're talking about carbon, like carbon-14 has 2 more neutrons than carbon-12 does. So those 2 neutrons have to like pack themselves in. And there's really, but this like spatial issue that comes into play. So as you start cramming more and more protons and neutrons and making bigger and bigger elements, you start to see that they're less and less stable. So lots of protons and neutrons decreases the stability of an atom. So Becquerel, and this is like really, it's only just over like 120 years old that this was actually discovered. So in the late 1800s, about 1900, Henri Becquerel, he extracted and isolated a sample of uranium from the ground. So the sample of uranium, he had it in the lab and he was trying to identify it. He was trying to determine like properties of this element. So he had it in the lab just sitting out like in a glass jar in the lab. So he had some photography film, so he was taking pictures of these elements as he was documenting this information. And he found that all the film that was near this sample of uranium, when he developed them, they looked like he had put them out in the sun. So they came out completely white, as if they had been like way overexposed. So he thought he got some bad film. So he went and he got more film, brought it back to the lab, went and used it, developed it, turned pure white, like someone had just like shined it up at the sun. So he's trying to figure out, well, what in the world's going on? So he took the photographic film and he started putting photographic film all around the lab, just unexposed photographic film, like still in its little box, okay? Not used at all. And he found that the film that was close to this rock sample was overexposed. The film over in the other room was okay. The closer he got to that rock, the more exposed his photographic film was. So he said, there has to be something coming from this sample. There is something going on with this rock sample that's different and unique. And he came up with this idea, this rock sample is releasing energy. The energy is exposing the film just like sunlight. So the energy is causing this change. And that was really when they first defined something as being radioactive. So isotopes with more neutrons than normal tend to be less stable. In order to become stable, they undergo what is called radioactive decay. Radioactive decay is the breakdown of an atom into more stable components. Okay, so isotopes that are not stable because they have lots of neutrons will spontaneously break down and release this energy in a process called radioactive decay. So they call these isotopes radioisotopes. So that just indicates that these are like less stable isotopes, less stable atoms. All of the isotopes of elements with atomic number 83 and greater are all radioactive. So if you look on your periodic table, 83 and up, none of them are stable. Why? There's too many. Too many what? Neutrons and protons crammed into that nucleus. So if you have 83, that means you got 83 protons, okay? You probably have at least 83 neutrons. So try cramming 166 protons and neutrons into an atom into like that 1% core. So that causes too much sort of like instability, shuffling, shifting that goes on in the nucleus, and that's what leads to this radioactive decay. Some of the smaller elements also have radioisotopes, like carbon-14. So what do these do? So when these break down, we're going to talk about 3 of them. We're really not going to talk about the other 2 because they're really minor. The common ones, the ones that are used in medicine, the ones that are used in like medical diagnostic, as well as those used in therapeutic, like someone getting radiation treatment, these are really the alpha, beta, and the gamma forms of decay. So we're going to talk about these 3 different types. The first one's alpha. So alpha decay is what happens when an unstable element breaks down. When it does, it actually shoots a helium nucleus out of its nucleus. So that means it's releasing 2 protons and 2 neutrons from its nucleus. They call that a helium nucleus. because that's what helium is. If you look at periodic table for helium, you see that it's 2 and 4. So normal helium would have 2 neutrons and 2 protons. So uranium does this. This is the first decay that uranium undergoes. So uranium-238, if you look all the way down the very last row on your periodic table, like those 2 rows way down at the very bottom, 3 across, find 92, and you'll see uranium. So when uranium breaks down, it starts spitting these helium particles out. What's going to happen to the mass of that uranium? If it spits out 2 protons and 2 neutrons, the mass will go down by 4. So we're going to decrease the mass by 4. So instead of 238, now it's what? 234. But it's also ejecting 2 protons as part of that particle. So what happens to the atomic number? It's going to decrease by 2. So instead of 90, what is it now? Or sorry, instead of 92, now it drops to 90. So is it uranium? No. Now what is it? What's its symbol? Look on your periodic table, find element 90. It's thorium. It's TH. So in this alpha decay, atomic mass goes down by 4. That's the top number. And it'll always be written in this symbolic notation style. So the atomic mass goes down by 4. The atomic number goes down by 2. And that element, it's a new symbol. So you're going to have to figure out, find the atomic number, and put down the new symbol. So you try the next one. So the next one's californium, CF. Not one that you would have had to know. There's berkelium, californium. So again, this is really big atom, undergoes alpha decay. What's its mass now? 253. What's its atomic number? 96. So the top number goes down by 4, bottom number goes down by 2. Then you got to look at the periodic table, and what's its new letter? CM, which stands for curium. So Marie Curie was one that worked with Becquerel and her husband, Francois. So she actually isolated a sample of radium. She named it radium because it glowed in the dark. Okay, so she thought that was pretty cool. So they extracted this from lots of earth. So you like dig up a whole lot of rock, and then you isolate, sort of dissolve away other components so that you can separate and identify individual substances found. So she found radium, she put it in a jar, she thought it was like cool, like a nightlight, she slept with it next to her bed. Well, she ended up dying of lymphoma, which was a cancer probably caused because of exposure to high levels of radiation throughout her life, because they didn't really understand what this did. Yeah, they used to paint the watch dials like on pocket watches so they would glow in the dark. So that, you know, like we now have like light reflective type of dials on watches so that, you know, like if you look, it'll still like glow in the dark kind of stuff. But they used to use radium, and they used to paint people to paint the dials, to paint the hands on the watches. And so those people all ended up with like mouth cancers and bone cancers and everything else. Yeah, all because they didn't really understand what it actually was. But yeah, so she was another one that was like she was like super bony, skinny. By the time she, like all the pictures I ever saw, I was like, oh, she looks almost emaciated. Like she like ended up having major issues throughout her life. Did some really interesting work, but things have changed in the last 120 years. So this is really one of the newer sort of branches of chemistry, just because this was not really understood until we started having equipment that we could actually monitor things, you know, and had to be equipment a little better than just photographic film. It had to get a little fancier than that. So that's alpha. So you'll see alpha sometimes written like this. So alpha is sort of an odd, it looks like a fish. That's sometimes called alpha decay. It looks almost like a fish without the sort of end on the tail. Beta, they do kind of like this bee with this foot sticking down is referred to as beta. So this one, what happens in the nucleus is that a neutron breaks down. So a neutron breaks down and it actually spits an electron out of the nucleus. This is beta decay. So this means if a neutron, we have a neutron in the nucleus, actually becomes a proton and an electron. And the electron comes out of the nucleus, but the proton stays behind. So you can think like here, a neutron is converted to a proton. So if a neutron is converted to a proton, the same atomic mass exists. This is why when they do the little symbol for it, see the 0. The mass doesn't change because a neutron converts to a proton. But what happens to the atomic number? If we take a neutron and convert it to a proton, we're adding a proton to the nucleus, so the atomic number will increase by 1, okay? So no change in mass. So the top number isn't going to change. That's where the 0 with the little E symbol. But the atomic number will increase by 1. So carbon-14 breaks down this way. So that extra neutron in there makes it less stable. So when carbon-14 breaks down, one of those extra neutrons converts to a proton. What happens to the mass? It's the same. What happens to the atomic number? So it is 7. Look at your periodic table. What is this element? Nitrogen. So in that, so like, can you see like 7 minus 1 would be 6? And so that negative is referring to the negative electron that's being shot out of the nucleus, okay? But I always think of it as actually meaning that. So if I took the 7 from the nitrogen and took away the 1, then that would make what it was originally, okay? Or 6 is a minus 7 plus, or minus 1 plus 7. Okay, so they would balance still on both sides. So what do you know about this isotope of nitrogen? Is this stable? Yeah, in fact, it's the most common isotope, right? So if you look at nitrogen, see it's a 7 above, 14.01 below. See, this is the most common. So this, 7 protons, 7 neutrons, 7 electrons, that's a nice even number of all of them. This is going to be a stable element. And that's really why this radioactive decay occurs. It occurs to try and create a stable element. Last one. So Cu, which is what? Copper. Very good. So copper, 66, 29. What would be the mass? 66. Mass doesn't change. So that 0 above tells you the mass doesn't change. But 29 goes to 30. Periodic table says, well, 30 is not copper, 30 is zinc. Now you have a closer balance between protons, neutrons in the nucleus of the atom. So this zinc 30 or zinc 66 is more stable than what that copper was. So they oftentimes, they'll call this, you'll see that little B for beta decay. Last one. And I told you, don't worry about positron. I took the questions about positron decay out of your dynamic study modules and such. Gamma. Gamma is the easiest one because gamma is really the energy emitted when protons and neutrons shift inside of the nucleus. So they sort of like shift around, trying to like become more stable by position. Gamma is this just energy. There's no particle that comes out. There's no change in mass. There's no change in atomic number. So that's why I said this one's the easy one. It stays the same. So if plutonium-250 undergoes gamma decay, that means the mass doesn't change, the atomic number doesn't change, the symbol doesn't change either. But this signifies that energy. This is energy that is higher than an X-ray, okay? Higher energy than an X-ray, but it's the same, so 250, 94 Pu. This energy can be used to heat a sample of water to the point of boiling, which can run generator turbines. This is what you use in nuclear power. Using or harnessing this energy, converting it to thermal energy, converting it to electrical energy. This is basic power plant. Really high energy from things like this plutonium. Uranium's another one that releases a lot of gamma energy. And so those are those radioactive rods that they use in nuclear power plants because of this high amount of energy released. So this is really greater than an X-ray. Alpha and beta are not. So this is like the highest amount of energy released.
So how are we able to consistently make them unstable enough to produce batteries?
So there are artificially or man-produced, and that's like there's concern about a lot of countries trying to be able to produce radioactive substances for like nuclear warheads and that type of thing. And so some of that is extracted. So there is in the ground, there are small amounts of this. So you could take where there might only be like 2 grams per ton of dirt. So you might be really, really small amounts, but if you can take and collect that and purify it, then you would have that. Nowadays, what like the United States and other countries do is we actually synthesize these unstable elements by smashing atoms together. Okay, so yeah, it's a chemistry thing. So by pushing these atoms together, forcing them, you can make these bigger elements, but they're not stable and they're going to break down. And so in that, we then harness that energy and convert it to heat and then electrical. All right, so you tell me, here's a practice. Yep. So if it is alpha, you will always see this. Okay. If it is beta, you will always see this. Like that's always a product. So that's like a nice way to like be able to say, oh, I know what that one is. So if you see the helium nucleus, then you know that it's alpha. If you see the little electron in the -1, then you know it's always beta. And if you see this little symbol, and oftentimes you'll have this and this, then you know that's gamma. So this one's alpha, this one's beta, this one's gamma. Oop, that's not a gamma symbol. That's a delta. Looks like that. Okay, so first one, atomic mass is 218. Atomic number, 86, which is Rn, yeah, radon. Capital letter for R, lowercase for N. Make sure that you always keep your the second letter is always lowercase. K42, what happens? Atomic mass, still 42, doesn't change, right? But atomic number is now 20. And that makes it calcium, Ca. And then the last one, Stays the same. So 125, 53, I. It's actually hopefully less, right? So we're talking, so what that symbol is really representing that energy. And in fact, some elements undergo alpha decay, also release gamma energy. Undergo beta decay, also release this gamma energy. So it's not like one, gamma can be like associated with other decays at the same time. So a bit about X-rays. So X-rays do not actually have a radioactive substance like in the room, like when we were talking about like Becquerel, where he had his little lump of uranium that was causing all kinds of photographic problems. So it's not that it has a radioactive substance. However, X-rays shoot electrons, which is really particles of energy, at a metal, which stimulates this metal and causes the metal to release X-rays. The metal is usually tungsten. So like you go get your like a dental X-ray done, or if you think you've got a broken arm, I gotta go do an X-ray. What they use is the machine actually generates a high beam of energy. It bounces off of a metal. That metal, because it's energy, like basically the metal almost becomes like energized, and that's what releases energy. So the energy, well, here's your funny looking hand, right? So everybody knows you've got bones. There's your radius. Here's your ulna. All those years of AMP. Okay? So you think that you have a fracture, right? So you think that that bone is damaged. The way that they tell, they put a piece of photographic film. Now everything's digital, so it's instantaneous and you don't have all the film waste. But you put a piece of film behind and you focus the machine so that it actually exposes that area. And they try and expose as little as possible because it is energy. But the films have gotten so sensitive now that the amount that you're exposed to is about 1,000 times less than what you would have been exposed to even 50 years ago if you went and got an X-ray done. So the film is super sensitive. X-rays are blocked only by hard material. It has to be dense and hard, and for you, that's bone. So it'll pass through soft tissues. So it passes through muscle, passes through skin, passes through vessels, but it won't pass through bone. But if there's a crack in the bone, then that means there's going to be fluid in that crack, and that X-rays will pass through. So that's how they can actually adjust that exposure. So it was like in one of the World's Fairs, I want to say it was like 1920, people were going and getting their hand X-rayed. Because it was like this new phenomenon when they started developing like X-ray machines and being able to do this. So you had to take your hand and lay it on that photographic film and sit there for about 5 minutes. Like you had to have that much exposure in order to expose the film, and then you could see the outline of your bones. And so that was like super neat and cool and everything. But the amount of energy that you were actually exposed to, super not safe. But again, didn't really know. Weren't really sure about all of that. As time has gone on, understanding about safety has dramatically changed. Yes, there you go. Well, that just makes the paint stick better. It really does. It actually makes that paint like stick to the wood surface better, way more durable. But it tastes good, so little kids eat it. Yeah. Mm-hmm. Well, yeah, there was melamine plates, which were these plastic kind of plates that my girlfriend has one from when she was a kid they ate off of. And the pigment actually has a radioactive chemical in it, like radioactive metal in it. So like her Geiger counter at work would like go beep, 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 when she was like, see, this is why we keep this in the lab. And I was like, you ate off of this as a child. Fabulous. So why is this an issue? Like, why do you really, one, care about this? So one, as a nurse, as a vet tech, as a dental hygiene, you're going to come in contact with ionizing radiation sources. Ionizing radiation is the energy that's released by all of these, released by alpha, beta, gamma, and X-rays. What ionizing energy can do is that it can interact with living tissues, interact with molecules in the living tissues, and actually cause them to become less stable. So if it reduces their stability, that could cause a reaction to occur that otherwise would not have. That could cause an error in a process that the cell is doing. That could lead to that cell dying. That could lead to that cell becoming an abnormal cell and not functioning like it should. So like I said with Marie Curie, so she died of lymphoma. Lymphoma is a cancer of the lymph nodes. And so that happens when white blood cells are exposed to high levels of ionizing radiation, and some of those cells die, but all it takes is a couple of those cells to become abnormal and begin to grow without control. So that's the concern and the reason that you want to understand and protect yourself from exposure, because you may be in a field where you're actually taking care of patients that may have a radioactive injection, that may have radioactive implants, that may be undergoing radiation treatment. So understanding the effects of this type of energy is really important in keeping yourself safe. So in order to keep yourself safe, things that they do, people that work in like the radiation lab, they always wear lab coats. You may use goggles, gloves. They may stand behind a shield of some sort. Oftentimes, they have a film badge. So it's kind of like Becquerel. So they have like a little badge that they wear that would be exposed if there's higher than normal levels of ionizing radiation. That will expose that film. So you wear this for 30 days, and then you turn it in and get a new one. They can determine how much energy you've been exposed to as part of your occupation. And if you've been exposed to a certain threshold, then they by law now have to move you to an area where you're not going to be exposed for a certain period of time, to sort of limit the amount of exposure over your job, to make sure you're not the one like taking the hit. Make sure that you're going to have minimal exposure risk. So my mother's an RN, and like she had patients that had cancer patients. So they would have radioactive implants put in, like in their bowels and such. And so she was like, they never said anything. That was never part of their training. Like, okay, well, you have a patient that, so therefore secretions, wound care, all of these aspects, like understanding like what you're actually taking care of. She was like, nobody ever said this. This was all like later afterwards that they started coming up with these regulations. So you now going into these fields are in a much better position than people were 50 years ago, because there's a lot more that's understood about it. So if you are looking at, and of course now it wants to freeze, looking at alpha, beta versus gamma, they also have different energy levels and require different protective shieldings. Right? So we talked about alpha, beta, gamma, and we said gamma and X-rays are kind of similar. Gamma is actually stronger than X-rays are, and we really didn't talk about the neutrons one. But in this, if you are exposed to alpha energy, this is the sort of rule of thumb is the stronger it is, the easier it is, or the bigger the particle, the easier it is to block. So alpha decay is that helium nucleus. You can block alpha decay with a piece of paper. So most of the time they take a piece of aluminum foil and you can cover your sample that's undergoing any kind of alpha decay, and that's enough to keep it from being able to expose you to any radioactive energy or ionizing energy.
And that's because the molecules of the alpha are larger. So
Big things don't go very far. So if you stay about 6 inches away, You're not going to be exposed. It just doesn't have this penetrating power. If it comes in contact, it's only going to penetrate like cells like close to it. So it's a really short distance type of ionizing radiation. So really the skin will block it. It won't penetrate through layers of the skin, just those couple 5, 10 layers of the skin surface. Beta, on the other hand, beta can actually penetrate through the skin and into deeper tissues. So to block beta, they'll use like that heavy duty aluminum foil, or they'll use a piece of plexiglass. So, you think of like the hockey games, like the plexiglass, it's usually like about 1/4 to 1/2 inch thick. That is a common shield that's used with something that's undergoing beta. This goes through the skin and into soft tissues, but doesn't go all the way through, because that's what gamma and x-rays do, right? So we said x-rays can pass straight through soft tissues, only get stopped by bone. Gamma just goes straight through all tissues. So gamma, really the only way to block is using lead. When have you used lead or had lead used on you? You've gone to the doctors. Yeah, so they put the apron, right? So they have that big heavy apron that they put on you. That is it's just over 1/4 inch of lead. So that's what that apron is, that's super heavy. So the lead apron is used. They can also use concrete. So a couple feet of concrete is also very effective at being able to block, because this passes through the body and along the way has the potential of causing ionizing radiation changes throughout its travels. So remember, I told you gamma doesn't even have any particles. It's nothing but energy. So just energy, no particles, passes the furthest. Whereas the one like alpha, which has that helium nucleus, really slow moving, easy to block.
So how come when you get x-rays, they don't like suit over your entire body except for your x-ray?
So what are they really trying to protect with a lead apron? There's really some very specific parts of your internal organs. Any ideas? Sometimes they have like the full body one, the one that like goes up over your shoulders and goes all the way down into your knees. But I've also seen ones where they only just put it like a little, like it looks like a little skirt kind of thing. So it just goes around your waist and down, because they're trying to protect your reproductive organs. Okay, so eggs and sperm, the cells that develop into eggs and sperm, if they get damaged, what is that potentially going to do? Yeah, lead to offspring that would end up with genetic diseases, okay, with abnormalities, might cause a mutation in eggs and sperm. And so that's why that's the most important, okay? Although now they have finally started putting like a neck shield. I don't know if anybody has ever had a neck shield on. Neck shields are to protect your thyroid. Okay, so your thyroid gland, which controls metabolism, we're going to talk about, it is sensitive to this type of ionizing radiation. And that's only been in the last 5 years. So like I told you, this has been around for about 120 years, but they're still seeing some things that are higher risk in terms of exposure. One, what they call the gonads. So that would be the ovaries and testes. You want to protect those, but they also have come to recognize that that soft gland of the thyroid in your neck is also one that can be sensitive to damage, to injury because of this. Yep, and that's why, it's because of that. So we'll talk a little bit more about some of the diagnostic and therapeutic and then half-lives on Thursday, and then I'll finish up chapter 2. All right, do make sure that so we're at like slide 26, so we're a little more than half done. So a lot of these are just like problems that we've got to do. You should be able to finish your post-lecture chapter 1 finish any of those, the dynamic study modules, you can look at and work on the radioisotopes because it's all about alpha, beta, gamma. So it's asking about like identification of these. So you can work on those in mastering chemistry. Start making your list of things to put on your note card.